Hello, welcome to my presentation. It's Elif Duygu Akvardarlar. I am a student of mechanical engineering in Ege University. Introduction to Nanoscience and Nanotechnology is my lesson this semester. Today, I'm talking about nanotechnology, nanosensors, and nanocantilever. Also, we have a question. Question is, can nanosensors warn of tsunamis and nanocantilever sensors? Let's begin. First of all, we are talking about the nanotechnology. Nanotechnology is science, engineering, and technology conducted at the nanoscale, which is about 1 to 100 nanometers. Nanoscience and nanotechnology are the study and application of extremely small things and can be used across all the other science fields, such as chemistry, biology, physics, material science, and engineering. Nanotechnology expresses the estimated power to create substances from the bottom up using tools and techniques developed to make full and high-performance products today. Nanoscience and nanotechnology involve the ability to see and to control individual atoms and molecules. Everything on Earth is made up of atoms. The food we eat, the clothes we wear, the buildings and houses we live in, and our own bodies. Who invented nanotechnology? The concept that since nanotechnology were first discussed in 1959 by renowned physicist Richard Feynman in his talk, "There's plenty of room at the bottom." K. Eric Drexler used the term nanotechnology independently in 1986 in his book Creation Engines: The Compounding Period of Nanotechnology. This book has suggested the idea of a nanoscale converter that can create a copy of both self and other predicted complexity items with atomic control. In this way, the emergence of nanotechnology as a branch of science in the 1980s was the unification of theoretical and practical affairs. What are the types of nanotechnology? Nanoparticles can be classified into different types according to the size, morphology, physical, and chemical properties. Some of them are carbon-based nanoparticles, ceramic nanoparticles, metal nanoparticles, semiconductor nanoparticles, polymeric nanoparticles, lipid-based nanoparticles. So, now we are talking about nanosensors. What's the nanosensors? First of all, I'm explaining the sensors. Sensors are devices that detect and respond to data from external environments. The resulting outputs are signals that are converted into human-readable displays or transmitted electronically for further processing. The invention of sensors has yielded very effective results in finding the source of problems in the medical science, manufacturing industries, automotive world, and some other fields. Now, let's see how nanosensors are. Nanosensors are sensors used in chemical, surgical, and biological fields to collect nanoparticle data that cannot be obtained by normal sensors. They are sensors that are much smaller, much lighter, portable, and can even be combined with smartphones for measuring heart rhythm, for example. Nanosensors work like normal sensors, but the difference is that nanosensors can detect small particles because normal sensors cannot do this. Nanosensors are used for computer chips, nanorobots, and other nanoproducts that we need to detect small particles to investigate. Sensors help solve problems, from detecting disease to protecting the environment. Normal sensors can be used to identify disease up to a certain limit, but these sensors cannot provide information about cell level. However, nanosensors can reveal the root cause and even the level of the problem. For example, nanosensors help detect harmful toxic elements in the air that normal sensors cannot detect to control the environment. They are high sensitivity, low cost nanosensors that can quickly detect changes in carbon monoxide level. The biggest advantages of nanosensors are that they provide us more accurate data than normal sensor. Viruses, an organism that cannot be identified with normal sensors, can easily detect with nanosensors. Nanosensors can measure the temperature of living cells. Therefore, they give more accurate results in the treatment of a patient than normal sensors and can save time on starting approximate treatment. As a result, the advantages of nanosensors for normal sensors are as follows: faster answer, more data, higher data accuracy rate, less impact on the measured case, more deep information, the best of current science. Remember, nanosensors are an extremely small device that can detect and respond to physical stimuli at a billion of a meter. Now we can answer this question. Question is, can nanosensors warn to tsunamis? And a tsunami is a large ocean wave that is caused by sudden motion on the ocean floor. This sudden motion could be an earthquake, a powerful volcanic eruption, or an underwater landslide. The impact of a large meteorite could also cause a tsunami, like these pictures. As it knows, tsunami is one of the most destructive disasters in the world. It is impossible to prevent the tsunami disaster, and it is very difficult to control it. But is it predictable? Yes, researchers say this may be possible. Now, new technologies like nanosensors with the ability to detect even a 1 centimeter rise in waves could forewarn coastal areas of tsunami, said the professor of Department of Electrical and Electronic Engineering in University of Melbourne. Nanotechnological inexpensive sensor that can detect invisible, odorless, hydrogen leaks, and sounds. The alarm wirelessly could help safeguard future vehicles and refueling station based on the gas, experts told UPI's Nano World. The objective of warning system is to continuously monitor the state of the sea surface in near real time. This allows for a fast and efficient warning to be issued through the correct channels. The warning system consists of three components: scientific instrumentation, communication system, warning system. And the scientific instrumentation is an assortment of sensors designed to detect various ocean activity, pressure, currents, velocity, and seismic sensors are the types of sensors used in effective tsunami warning system. Some sensors target the tsunami wave over different ocean depths by measuring wave height. In order to do this effectively, the sensitivity of these sensors must be sufficient enough to detect change in wave heights of a few decimeter over deep ocean. For example, ocean waves consist of different frequencies and amplitudes that are normally stable and predictable. And in addition, all other environmental factors affecting the sea level must be understood and monitored in order to separate these signals from the tsunami wave. The wavelength of tsunami waves is different from wind-driven and tidal waves. This allows for the identification of tsunami by using spectral analysis, a process that identifies variation in seismic components over a period of time. Spectral analysis uses wave heights versus time to determine the normal frequencies and identify changes or abnormalities. Once the observation of seafloor bottom pressure sensors, global navigation satellite system, and tide coast or satellites have been called. A fast transmission of the data to a progressing center is required. For this purpose, radio transmission from a buoy to a land station is used. If the distance between the two antennas is greater than about 50 kilometers, a satellite link is established. The progressing centers at the land station analyze the incoming data and detect potential source of tsunamis, and combine this with the retrieved observation. The results are the basis for the activation of a warning system. Now we are talking about nano-cantilever sensors. Cantilevers are typical rectangular shaped bars of C less than 1 nanometer thick. Adsorption recognitions of molecules on the surface of such micromechanical cantilevers functionalized with receptor molecules result in bending of the cantilever. Because of the surface stress, the bending is detected by deflection of a laser beam. Cantilever sensors can be operated in various environments, such as vacuum, air, or liquids. The major advantage of such miniaturized sensors are their small size, fast response times, high sensitivity, and direct transduction without the need for any labels. Scientists said that some of the information gained here would be necessary for the proper design of the future nanomechanical sensors using the console. In this picture, this second picture about schematic of the atomic force microscopy technique. Nanocantilevers have become key components of nanomechanical sensors that exploit changes in their resonance frequency or static deflection in response to the environment. It is necessary that they can operate at a given but adjustable resonance frequency and or static deflection ranges. These are my resources about this presentation. And so, thank you for listening to my presentation. Have a nice day.